out at the frozen edge of our solar system, nearly 3 billion miles from the Sun, orbits a world of staggering mystery, Neptune's largest moon, Triton. On its surface, it's one of the coldest places we've ever found. But what if this frigid wasteland is hiding a secret? What if, beneath miles of ice, there's a vast, dark ocean with the potential for life? The clues are startling. You see, Triton isn't just another moon. It's an outsider, a cosmic rebel. No other large moon in the entire solar system orbits its planet backwards, completely against the direction of its spin. That bizarre retrograde orbit is our first major clue that Triton isn't what it seems. It wasn't born here, in the cold shadow of Neptune. It was captured. Scientists are convinced Triton was once a dwarf planet, a lot like Pluto, that spent its early life peacefully orbiting the Sun out in the distant Kuiper belt. Billions of years ago, it wandered too close to Neptune and was violently snagged by the ice giant's gravity. That cataclysmic event set the stage for one of the most intriguing stories in our solar system, a story that could turn a frozen exile into a top candidate in our search for life beyond Earth. The frigid, hostile surface. To really grasp why Triton is so special, you first have to understand just how brutal its surface is. When NASA's Voyager 2 spacecraft flew by in 1989, it clocked surface temperatures at an almost unbelievable minus 235 degrees Celsius. That's just a few degrees above absolute zero, the point where atoms themselves nearly stop moving. It is, by far, one of the coldest surfaces we have ever measured. Picture a world sculpted from frozen nitrogen. That's Triton. Its surface is a thick sheet of nitrogen ice, mixed with water ice and frozen carbon dioxide, or dry ice. This isn't a world of rock and soil, but a brittle crust where the very ground is made of things we normally think of as gas. If you were standing on Triton, the sky would be a near-perfect vacuum. The atmosphere is impossibly thin, with a surface pressure about 1/70,000th of Earth's. It's mostly nitrogen gas that's literally boiling right off the ice, along with tiny traces of methane. And yet, this faint atmosphere is surprisingly active. Voyager 2 spotted thin clouds of nitrogen ice and hazes of organic gunk which form when sunlight zaps the methane in the air. But this offers zero comfort from the cold. There's no atmospheric blanket to trap warmth. Any heat that makes the long journey from the Sun is immediately radiated back into space. From this perspective, life seems completely impossible. The intense cold would slow down chemistry to a crawl, and the total lack of liquid water on the surface is a deep. For decades, Triton was seen as beautiful, but data cryogenically frozen relic at the edge of everything. The Voyager 2 revelation, that all changed on August 25, 1989. After a 12-year journey, Voyager 2 zipped past the Neptune system, coming within 40,000 kilometers of Triton. The data it sent back across billions of miles of empty space was revolutionary. It completely shattered the image of Triton as a dead world, and replaced it with a portrait of a geologically active, dynamic, and deeply mysterious place. Two discoveries, in particular, changed everything. First, the surface was shockingly young. When scientists want to know how old a surface is, they count the craters. Over billions of years, a planet or moon should be covered in impact scars, but Triton was eerily smooth. On the 40% of the surface that Voyager 2 could see, it found only 179 clear craters. For comparison, one of Uranus's moons, Miranda, has over 800 craters despite having only 3% of Triton's surface area. This lack of craters meant something was actively erasing them. The surface, scientists now estimate, is less than 100 million years old, maybe even as young as 10 million. Geologically speaking, that's yesterday. This was the first sign that powerful forces were at work, resurfacing the moon from the inside out. The second discovery was even more stunning. As Voyager's cameras scanned the southern polar region, they saw massive plumes of dark material erupting from the surface, soaring miles into the thin atmosphere. These geyser-like jets, which we now call cryovolcanoes, were spewing nitrogen gas and dark dust up to 8 kilometers high, where faint winds would catch them and drag them for over 100 kilometers. This was the first time active plumes had ever been seen on an icy world. One theory was that the sun's weak light was heating a layer of nitrogen ice from underneath, causing it to burst. But a more exciting idea was that they were powered by heat from Triton's interior. The sheer amount of material being thrown out hinted that these geysers were connected to something much, much bigger deep below the surface. a young surface and active geysers. These two facts just didn't fit with the picture of a simple, frozen moon. Triton wasn't dead. It was geologically alive. The question was, how? Unraveling the mystery. How is this possible? So, how can a world this cold and this far from the sun be so active? The answer is tangled up in Triton's violent past. When Triton was first captured from the Kuiper belt, it would have been thrown into a wild, stretched-out orbit. As it whipped around Neptune, the planet's enormous gravity would have squeezed and flexed the moon relentlessly. This process, called tidal heating, would have generated a colossal amount of friction and heat deep inside Triton. For a long time, the thinking was that this intense heating would have been stopping soon after Triton's orbit settled into the nearly perfect circle we see today. But newer models show something fascinating. As the tidal forces heated the interior, melting some of the ice, that slushy ice shell would have become even more deformable, trapping the heat and keeping the process going for far, far longer than anyone expected. A 2024 study suggests this internal furnace could have been blazing for 1 to 4 billion years. For billions of years, Triton wasn't just warm inside. It was roiling with energy. The heat was likely so intense that it kept the outer ice shell incredibly thin, maybe only a few kilometers thick, and constantly fractured it, creating a direct connection between the surface and whatever lay below. But that's not the only heat source. Triton is big enough for its heavier stuff rock, a metal to have sunk to the center, forming a solid core. This rocky core should contain radioactive elements. As these elements decay over eons, they release a slow, steady trickle of heat. This 1-2 punch of ancient, prolonged tidal heating and ongoing radioactive decay could easily provide more than enough energy to power the geysers and resurfacing we see today. The hidden ocean and all of this internal heat points to one staggering possibility. If Triton's interior has been warm for billions of years, and it's made mostly of water iced, it raises the incredible possibility that a vast layer of that ice melted. Hidden beneath its frozen crust, Triton is very likely an ocean world. The picture scientists have now is of a world with a rocky, heat-producing core at its center. Surrounding that core is a massive, global ocean of liquid water, maybe up to 130 kilometers deep, and encasing it all is the outer shell of ice we see from space. Strange features on the surface, like the bizarre dimpled cantaloupe terrain, are thought to be caused by blobs of warmer ice pushing up from below. More evidence that something is moving under the crust. But how could an ocean stay liquid in that cold? The secret ingredient is probably ammonia. We know objects from the Kuiper belt are rich in ammonia, and since that's where Triton came from, its ocean is likely full of it too. Ammonia is a powerful antifreeze, radically lowering the freezing point of water. Models suggest Triton's ocean could be a liquid at a mind-boggling -97 degrees Celsius. For us, that's unimaginably cold, but it's still a liquid. In fact, some new research suggests that even after the main tidal heating died down, there might have been one last burst of activity. As the ice shells slowly thickened and froze, it could have squeezed the ocean beneath it, building up immense pressure enough to crack the crust wide open and push a slushy mix of water and ammonia to the surface. This could be exactly what created Triton's incredibly young, freshly paved landscape. The evidence points to a dynamic world, where a hidden ocean has shaped the face we see today. We've gone from a frozen wasteland to a world with erupting plumes, and a strong case for a hidden ocean. It's a place that completely redefines where we think liquid water can exist. If you find mysteries like this as fascinating as I do, take a moment to subscribe and join our community of explorers. There is so much more of the cosmos to uncover together. The ingredients for life, the potential for a liquid water ocean, even one this cold and dark, forces us to ask the ultimate question: could it be habitable? Could something actually be living in this alien sea? To even begin to answer that, we need to look for the 3 key ingredients for life as we know it: liquid water, essential elements, and an energy source. Incredibly, Triton seems to have a shot at all 3. First, the water. We've just laid out the strong case for a long-lived super-chilled ocean, full of ammonia, antifreeze. That checks the most critical box. Next, the elements. Life on Earth is built from a handful of key elements, like carbon, nitrogen, and oxygen. Triton's very nature suggests they're all there. Its interior is a mix of rock and ice. The rock provides minerals, while the ices provide water, nitrogen, and carbon compounds like methane. Better still, if the ocean is touching the rocky core, you can get chemical reactions that release nutrients, and create the exact kind of chemical gradients that microbes use for fuel in the dark depths of Earth. Even the dark material in Triton's plumes is thought to contain organic compounds, which could get cycled back down into the ocean, providing more building blocks for life. Finally, energy. With no sunlight, life would need to be chemosynthetic, heating energy from chemical reactions. The water-rock interactions on the seafloor are a perfect source for that. The heat from the core could also power hydrothermal vents, just like the black smokers on Earth's ocean floors that support entire ecosystems, completely cut off from the sun. Of course, the hurdles are huge. An ocean that's nearly minus 100 degrees Celsius is an extreme environment. Chemical reactions would happen at a glacial pace, meaning life itself could be agonizingly slow compared to here on Earth. The high ammonia content could also be poisonous to life as we know it. But nature is tough. Here on Earth, we've found microbes that thrive in extreme chemical environments and enzymes that still work at temperatures approaching Triton's. It pushes the boundaries of what we consider habitable and forces us to think outside our warm, Earth-centric box. Triton versus other ocean worlds. In the growing gallery of ocean worlds, Triton really is a unique case. It's often compared to Jupiter's moon, Europa, and Saturn's moon, Enceladus, the two top prospects for alien life in our solar system. Both are famous for their own subsurface oceans and have plumes that vent water into space. Europa's ocean is probably in contact with its rocky mantle, offering a rich chemical environment. Enceladus shoots spectacular jets of water and organic molecules into space, which the Cassini spacecraft actually flew through and tasted, confirming a habitable environment is there. Triton joins this exclusive club, but with a twist. Its environment is, by all accounts, much harsher. Its ocean is way colder than Europa's, and its energy supply may be lower. This leads some scientists to think the chances for life are lower on Triton than on its more famous cousins. But what makes Triton so compelling is its unique history. Its origin as a captured object from the Kuiper belt means its chemistry is fundamentally different from moons that formed with their planets. It's probably much richer in things like nitrogen, methane, and ammonia. That could lead to a totally different kind of ocean chemistry, and maybe a different path for life to even begin. Its heating is also different. Europa and Enceladus are warmed by the constant pull of their giant planets. Much of Triton's energy is a leftover relic of its violent capture. That unique history may have kept its ocean active for billions of years, giving it an immense amount of time to cook up something interesting. Triton may be a dark horse in the race, but it's a powerful contender, offering a glimpse into a completely different kind of habitable world. From the moment of its violent capture, Triton has been a world of conflict. It's a battle between the crushing cold of deep space and a fire burning within. It has a surface frozen to near absolute zero, yet it's alive with cryovolcanoes. Its backward orbit marks it as an exile, a stranger from another part of the solar system. And yet, this very history is what makes it one of the most exciting places to look for life. The evidence points towards the tantalizing possibility of a vast, dark liquid ocean beneath its ice-sand ocean that could have existed for billions of years. It seems to have all the basic ingredients for life: liquid water, organic stuff, and energy. The conditions are extreme, yes, but we've learned over and over again that life is tenacious. The glimpses from Voyager to back in 1989 were just the first chapter. They left us with far more questions than answers. Is the ocean really there? How deep is it? And what's really powering those bizarre plumes? Answering these questions means we have to go back. Mission concepts like Triton have been proposed to do just that. And although it wasn't selected, the dream of returning to Triton is still a top priority for scientists. A future mission could fly through those plumes, or use instruments to finally confirm the ocean's existence, potentially changing our understanding of life in the universe forever. Triton remains a ghost on the edge of our vision, a world of incredible promise wrapped in mystery. It's a reminder that the potential for life isn't just confined to the cozy, sunlit worlds near us. It might just be thriving in the most unlikely of places, in the cold, the dark, and the impossibly distant frontiers of space. So what do you think? Could a world as cold as Triton really be hiding life in a dark ocean? Let me know your thoughts down in the comments. If you want to keep exploring the most fascinating and mysterious corners of our universe, make sure to subscribe and hit that notification bell. Thanks for watching.